All right, hello everyone. Welcome back to COP-3402. Good afternoon. I want to begin by going over the homework and taking questions. Yes?
When we try to download the PDF for the book, by the way, it says you have to loan it.
You have to log in.
It says you have to loan it.
Oh, loan it. That should be fine. I was actually going to ask that. Is anyone able to download the book? I know one student accidentally downloaded the entire book. But I was able to download the book anyway, so I don't know if it's really a problem. Did you try pressing the loan button?
It just says to check out. And you have to select for a day.
A day. But it's not asking you to pay for it.
No.
Okay. I think I went through those steps.
Check it out.
Yeah. Try. Okay. I'm not sure who to ask for help with that, but try pressing that checkout button and.
Yeah, it lets me download it.
Oh, okay.
But it's just.
I have somebody who I can ask for clarification on that, but I think that's fine. I think that might be how it's supposed to work. Yeah, you check it out. It doesn't actually charge you anything, and you just can download the book in individual chapters that way. So, but thank you for bringing that up because I was actually curious if that was a problem or not. So I'll make a note to ask somebody about that. Okay. So, any questions before I go over homework 3? Does anybody have questions about what we reviewed last time? Version control using did? Has anyone started the VC exercise and was running into issues? Okay, so homework 3. Can anybody answer for me number 1? What? Number 1 on here, not the first one in the table, not the first row in the table, but the first question. You get an error. If you try to push to a remote and you don't have your changes synchronized with the remote's changes, you get an error. It's like you have a bank account balance with your bank, and they have a transaction history like we discussed in the last lecture, and then you suddenly want to tell your bank to reset your balance or start a new balance history. That's not going to work. Yeah?
Is that not what happened to you last lecture?
That is what happened to me last lecture. You're right, because I'd already created a copy of that. I already pushed changes to that remote repository, and I tried to push more. So you're absolutely right. That is the issue I ran into. And I for the second part of this question, how do I get my repo if I already deleted my local repo? I did not mention this command in the last lecture. However, the answer is in the VC project, or the VC exercise. So if you go through the steps in that exercise, you'll find the answer. And if you got this wrong, that's fine. As long as if you put get poll or you put something else, you'll still get full credit. But the answer is not, I did not say the answer last lecture because I just forgot to. It was not a command that just came up while I was going through the exercises. And these we reviewed last lecture. I'm not going to go over them. I'm not going to give the full answer here, but is anybody confused about any of these specific steps? Do they want clarification on any of these problems? Okay, so I'll move on. We can take attendance now then. Cool. So today we're going to be going over build automation, and I think many of you may not actually know what that even means. By building, I mean the process of compiling your source code, and by automating, I mean the process of making that automatic, using tools to automatically build your source code for you into binaries. And this is a topic that is still very prevalent in software engineering today. The tools we'll be using to demonstrate this are older tools, but they're still in use in C projects across the world. And really the concepts of automating your build system are still widely applicable today. I'm actually doing research in this area right now with Dr. Gazzillo about securing some of the steps of this process. So I'm going to actually drive this lecture with examples. So first, let's start by creating a C program. Go to my desktop here, make a directory called COP-3402 build automation. Maybe I'll actually, let's say we're making a math library. So a C program that has some math functions implemented. What I'm going to do is create two files, a main.c file. So I'm running my main program here. So let's say we're implementing a function to compute the square of a number. And maybe what I'll do here is actually say x equals 2, replace this with %d, we'll say x, and replace that with x. Okay, and what I'm actually going to do is make a new file here called square.c, and we'll make a function to actually implement this logic. Square. So the square of a number is just the number times itself. So we'll say x times x. And now, because C programs, you need a header file to incorporate logic from one function to another, one file into another, I'll define a header file called square.h, and I'll provide the prototype, the signature, the declaration of that function square. And in main, I'll include that function. And now, how do I compile this? GCC. What do I pass to GCC? Yeah, I can just pass every file. Oops. Oh, I know why. Does anybody know what the issue is here? I used angle brackets for square.h, not quotes. So if you use angle brackets, that says look for a system header on your machine. But square.h is defined in the same directory as main.c, so I need to use quotation marks instead of angle brackets. That was the issue. So now if I run this command again, you'll see it compiles, and if I run a.out, we get the square of 2 is 4. And I'll actually add a \new line here, so that way the .c and square.c, and then a.out. The new line character name. So it works. This is the way you all learned in Intro to C Programming, and probably in CS1 you use this technique of building C programs. If you weren't using an IDE, you probably just built them all at the command line directly by using calls to GCC. And yeah, let's say you want to give this program a name. I'll just pass the argument. What does the -o flag do? You give it a name, yeah. So if I wanted to call this, instead of a.out, I wanted to call it main, I could say gcc main.c square.c. And now if I run ls, you'll see there's a main file there. That's a binary. It's an executable binary specifically that we can run. So I'll remove that a.out file and now run that main file. And we get the same output. A little bit bigger. There we go. Okay. So what if I have two C files? Well, I kind of preempted that. We have two C files already. You have to pass them all to GCC, or CLang, or Intel CC, whatever compiler you're using, you want to pass them all to it. But this approach kind of breaks down quickly if you have many C files, like the Linux kernel. So I'm running Ubuntu on my machine, and that is a distribution of Linux. Linux itself is implemented in C, thousands of files. Do you really think Linux developers are running GCC with like 30,000 file names afterwards each time? No, they're not doing that. Sure, you can make this process a little bit faster by using up arrows to go through and recompile every time. But It's still not very optimal. What's one reason why building so many files at once would be bad?
It's a waste. You have as many individual files that have to be shared.
A waste of what resource?
System memory?
What?
Is it a waste of system memory?
Memory is one. What's the other one? We learned about this in CS1. What's the two resources you analyze with Big O?
I was going to say time.
Yeah, time. It's a waste of time. You're recompiling all these files every time. Let's say I make a change to main.c, or sorry, main.c, and I change this to, I don't know, 4 instead. If I run this command, I have to recompile square.c as well. But did I change square.c? No, I didn't. So I should avoid having to recompile that file as well. And this sort of illustrate or explains what I just was illustrating with this example. We want to take advantage of is the notion of separate compilation. Oops. Where was that? I just had it here. Yeah, separate compilation. So separate compilation, has anybody heard this term before? It's been around for like decades. It's kind of a standard in software engineering now. When you have a compiled program, so you're writing in a language like I don't know, Zig, Rust, C, C++. All these languages are compiled. You want to compile each individual compilation unit, each source file, and its header files that it includes separately. So that way, if you make a change to one, you don't need to recompile the entire program. You only have to recompile the one compilation unit, source file that you modified. And there's ways to break up this step using command line operations. So if I were to run gcc, let me see, maybe there's a step here that can show me this. Yeah, so before I say it, I'll put the correct slide up this time before I just give you the example. I'll leave this one up. The names here don't quite match what we have in our example, but the idea is correct. So you can use the -c flag to GCC to run the compiler to only compile the files. So we've been using GCC as a full compiler so far, but that's not really quite what GCC is. GCC is more like a language tool chain. It does more than just compile your files. After it compiles each file that you pass it, each .c file, it also links those files together to form a final binary that you can run in your machine. It's how the program essentially combines or compile main.c and compile square.c into the final main binary that we run. But if I were to run gcc-c and then pass it my main.c file, you'll notice we have this main.o file now. This is an object file. It's machine code. This is not something we can run on its own because main.c references a function defined, the square function here, defined in square.c. So what we need to do is gcc-c square.c. Now we have main.o and square.o. And then we can run gcc to actually combine these two files together. So I can say main square.o, main.o. Let me quit Slack. And now we have that main file like before. And what we've just done is separate compilation. We had passed GCC these separate object files, separate compiled binaries for each individual part of our program, and asked it to link them together. That's the step known as linking and compilation, which we'll go into later in the semester. But basically, compilation proper just converts source code, C code, into assembly code or machine code. And then linking is what resolves the symbols that one compiled object file references from another to form a final binary. And what this lets us do is only modify the files that we need to modify and only recompile the files that we modified when we're trying to recompile an entire program. We don't have to recompile the whole program every single time we run the program. or modify the program, I should say. And one thing I want to point out here is that GCC in this case, it is reading the extensions of these files to know whether or not to compile them as C code or to link them as object files. So the file extension is important here. And we could do this all manually. This is still technically something that we could do manually. So like I could, again, modify main.c. I could decrement this to 3 instead of 4. And now I could actually recompile main.c and then run or link this again, the compiled main.o, the modified main.c that was compiled, link this with main.o, run main, and we get the new correct program. I didn't have to recompile square.c because I didn't change it. So if I were to draw a diagram of this, I'll delete last lecture's notes. We have main.c at the top. I'll change that color to, let's say, black. Make it a little bit bigger, can I? Or I should say main, not main.c, but main. Main depends on main.o and square.o. And these in turn depend on the C files with the same prefix as these .o files. So main.o depends on main.c, square.o depends on square.c. And I'll draw some arrows here just to signify that relationship. So you can see there's a tree structure here. Again, topics from CS1 kind of reappearing in this course. And what we had done was, maybe there's a marker here, tool here. No? Oh well. We had modified main.c and only needed to recompile this branch of the tree structure. We didn't need to recompile the entire tree. Whereas if we were to run the whole command I had earlier, gcc, let's see if I can find it here. Yeah, right here. Recompiling from scratch both the C files, we would have to recompile both branches every time we run this command. And like some of you had said, that is a waste of time and memory to do that. So how can we do better? Well, maybe I could write like a bash script or something to have these commands in them, and maybe I could do some like checking of like file times when they were last accessed and write my own scripts to automatically build programs for me and do all that. But that's like a lot of work. It's very confusing, easy to get wrong, and really unnecessary because there's another tool that I'm going to introduce now called make. So make files. Has anybody used make files before? I think maybe like 1 or 2 people. Yeah, okay, yeah. So make is a way to achieve this sort of build automation that is the focus of this lecture. And make is kind of a primitive tool. It's sort of like a, it's kind of like a shark in the sense that it hasn't evolved over the course of millions of years. It's kind of already achieved a working state that people can use, so it has no more need to really change. And it's pretty old, but it still works. I'm going to actually make a make file here. Let me actually, what I'm going to do is enter a program called tmux. It's a terminal multiplexer. It lets me split my screen. You don't need to know this for this class, but it's going to be useful for me doing this lecture because I can have multiple terminal windows up at once. And I'm going to create a make file. So the standard naming convention for make files is either makefile all lowercase or makefile with a capital M. I'll just do the all lowercase option. And make files consists of these build commands or recipes. They consist of 3 parts. They have a target, so we'll say main is our target. And they have prerequisites, which I will not list yet. And they have a recipe for building those prerequisites. And one thing to keep in mind is that in make, you have to indent your recipes with tabs, not spaces, tabs. And I can show you this as a tab because if I run set list in Vim, you can see this sort of nonsensical content here signifies a tab character. So what I'll put in here is the command we ran earlier to build the main program. gcc-o main, and we'll pass it main.c and square.c. And what this lets me do is whenever I want to build the program main, I can just run make. And make will run the first rule in my file automatically for me to build make. And what's cool, or build main, I should say. And what's cool is that if I run make again, make will say main is up to date. There's been no changes to any of the files that main depends on, which right now is empty. Since the last time you ran this command, the main file already exists, so I'm not going to run this command again. So it actually saves you that time and memory that you were talking about earlier that was a waste. This is cool, but we can do even better than this because this tree structure still exists and we're not really exploiting it yet. And it's still, we're recompiling all the way from scratch here from the C files. And remember, if we recompile from the C files, we have to recompile the whole tree, which we should not have to do. So the first step to making this process more automated, there we go, I think that fixed it. Is to add dependencies to main. And what this will do is make it so that if I modify one of these files, main.c, let's say, and then run make, it ran this time. Even though the main file already existed, it still ran. That's because make will actually look at the last access timestamps of your files, last modified timestamps, and it will compare the target's last modified timestamp to the prerequisites last modified timestamps. Yes?
Are the prerequisites separated by tabs as well?
No, any kind of white space. Yeah, it can be tabs, it can be spaces. It doesn't matter for the prereqs. All that only matters is that they're on the same line. If you have a lot of prerequisites, you can actually use a backslash to denote the same line. So I could write this as well, and that would actually also be correct. But we'll forego that for now. So now if I run make again, you'll see it doesn't recompile it because there was no changes to the dependencies of main between the last time I ran make and now. But still, there's a problem here. Whenever we run make, we're still recompiling from scratch, all the .c files. So let's take a look at this tree structure, and we'll notice that main doesn't really depend on the .c files directly. It depends on the .o files. So we should really change this to .o. But now we're in a problem here. Let's say I remove I'll remove all the .o files. So I can say star.o. The star means wildcard. Any prefix followed by .o. I'm going to remove all those files. And I can actually show you this. If I were to type in echo star.o, you'll see that it actually prints out all the .o files in my current directory. This is something that bash has built in. It's not something inherent to echo or any other command. It's just a built-in feature of bash, these wildcard operators. So if I run rm star.o and then try to run make, oh yeah, it will work because we're recompiling from scratch. Let me try running it again here. Oh, I don't think I saved. Somehow make knows how to do this, which I did not ask it to do, but that's kind of cool. But interesting. So what I was expecting to happen was make would tell me that there's no way to build these .o files because it doesn't have any information on how to build them. I think make was able to automatically infer based off the file names how to build these files, main.o and square.o. What I'm trying to illustrate here, I'll have to illustrate it directly without make giving me a warning, is that you can actually specify a tree of dependencies with make. So I could say main.o depends on main.c, and to compile this, you run gcc -c main.c. And if you thinking it's crazy how fast I'm going with all these selecting commands, that's a reason to use Vim, because you can select blocks of text and copy and paste and move them around very quickly. Okay, so now, oops, there we go. If I run make, if I actually remove main, remove all the .o files, and then run make, you'll see it's now running the specific commands that I gave make to build those dependencies of main. So make will actually read this tree here. It has this tree structure in memory, and it will determine that in order to build main, it needs main.o and square.o. And there are rules already provided for building square.o and main.o, so it will follow those rules to build them as well. But if I were to move, let's say I moved main.c to, I don't know, test.c and then run make, it will say no rule to make target main.c needed by main.o. Stop. Make cannot find any rule to build a main.c dependency, and because we didn't provide it ourselves, it just runs into an error. So I'll undo that. I'll move test.c back to main.c. And you'll notice that I've been frequently running rm commands to delete the files that I've been creating, so I can kind of reset my progress with this example. There's a way to do that automatically with make as well. The convention is to define a clean rule. So the way a clean rule works is you specify a command in here to remove files. I'm going to say rm main, rm main.o, and rm square.o. And now I can say make, and you can actually pass a specific rule name to make. So if I press tab, it will autocomplete for me the names of all the rules in my make file. That's another reason to use tab completions. If you're in a C project that has a make file, just type in make and then press tab a few times. All the targets for that make file will appear, so you can know what to run. So I'm going to run make clean, and it works this time, and all my files are gone, all my generated files. It's a good idea in practice to define a clean rule that deletes all your compiled files, because these are things you don't want to push to version control. You don't want to add to your Git repositories, because somebody downloading your code can just build them themselves, as long as your program works. So a problem here is if I try to run make clean again, I'll get an error message. No such file or directory. Does anybody know how we can fix this problem? There's a flag to rm that we can use. So what we can do, I'm going to actually show you another cool thing with Vim. If I hold Shift and press K on a command, it opens up the man pages for that command directly in Vim. So I don't need to go to a separate terminal window and open up the man pages. It directly hops to them. And now I can just look for flags or options right here. Oh, what's the first option? -F, force. Ignore non-existent files and arguments, never prompt. So what I'm going to do is go here, use visual block mode, -F, there we go, it worked. And insert -F flag to all these rm commands. So now if I were to run make, or rm, make clean, it works every time, regardless of whether or not those files exist. So all our targets work without emitting errors, even if some of the files that they delete don't exist. But there's a catch here. Make is full of these little catch-22s. In fact, most build automation programs are absolutely horrible. Like, they're very weird to work with once you try and build sophisticated projects with them. Make is one of the simpler ones. If I were to create a file called clean, and then try and run make clean, what do you think is going to happen? what is the part before the colon in a make recipe? The target. So what is the name of this target? Clean. But a file called clean exists. So if I try to run make clean, it says clean is up to date. Your target already exists. I don't have to run these commands. But really, when we created this clean command here, we weren't saying we wanted to build something called clean. We wanted to create a command called clean, essentially. The way to tell make that a command name or a target name is really a command and not actually something you want to build is to create a .phony rule. This is just something specific to make. And what this will say is everything in the .phony list is not really a file we want to make, it's just the name of a command. So now if I run make clean, it works like before. Let's see, kind of already gone over this. Yeah, okay, that's a cool next step. All right. So I think this tree structure kind of illustrates the idea of how we're building this dependency tree. So the next thing I want to show is how we can make this even more automatic. Some more like make tricks. And you won't necessarily need these tricks for this course for the assignments because I'm going to be giving you a template make file for most of the projects. But I encourage you to learn make because it's kind of nice to know how to use make for a lot of your own projects, especially C projects. It helps you automate a lot of the steps in building them. And you don't need to use make only with C. All the things I've shown here, I'm compiling C code, but you can use with any programming language you want. And it doesn't have to be used to compile code either. You can use it for anything, really. So now, what I want to show is that these two rules here, they're kind of redundant. They're the same recipe, same target, same dependencies. The only difference is the names of the files. So make provides some facilities for making things like this a lot faster. It's wildcard matching. So what this will do, I'll select these and delete them, is tell make to generate any .o file, you need a .c file with the same prefix, prefix, both start with the letter P, with the same prefix, and then you will compile it by running gcc-c, and in make there's special variables you can access that begin with a $sign. $sign less than says the first dependency. So to generate any .o file that depends on a .c file with the same base name, you'll compile that file with the .c flag, with the -c flag. So now if I run make and press tab, you can see, actually I guess it doesn't appear, but I can create this. So I'll run make clean, and then I'll say make main, and it actually still works, just as before. One thing I don't like about this is that this is a little too permissive. It says any .o file. You can actually make this more specific by creating a variable. So I could say sources equals, and then a space-separated list of project sources. So I could say sources equals main.c, square.c, and then my object files are main.o, square.o, and I could say objects. And now what this says is to build any one of the object files in objects, I need to replace a prefix in that object file with the .c file with the same prefix. And now if I run this, oops, I'll run make clean again, it still works. So this is like a pretty standard makefile setup you'll see in a lot of projects. And I can actually change this to be objects, and this could also be objects as well. And yeah, it all still works. One more special variable you can use in this case would be $circumflex or caret, whatever you want to call that character. The technical name is circumflex. I'm a nerd, so I know it. And now if you run make again, it will still work. This special variable just says all the dependencies of this rule. So it'll expand to objects, and objects will in turn expand to main.o and square.o. Has anybody heard the term DevOps before? Yeah? Yeah? Or do you have a question, or were you just raising your hand to say yes? Okay, yeah. DevOps is about this sort of thing. Not make necessarily, but automating the build process for your code and the deployment process as well. Because when you're deploying code to a remote server for production, you have to build it in production sometimes too. You have to build certain parts of it. And DevOps is sort of a job title where all your job is managing things like make. Not necessarily make software, but software like make. That is responsible for building your code intelligently in a way that does not waste resources. Yeah, one more thing here. Since we have it in this chart, I guess I'll show it. It's a little confusing, but I'll show it. You'll notice there's still redundancy across these two parts because we're duplicating the base names of all these C files. If I had like 10 C files, that'd be really annoying because now I have to duplicate all those names. So one way around that is to use wildcard replacement. So I would say sources, let me see. The syntax is a little confusing, but I think I got it here. Yeah, it's on the right-hand side. This says take the variable sources, and for each item in that list, main.c, square.c, replace the name, cut off the suffix .c, and replace it with the suffix .o. And now, oops, let me run it here. You can see it still works, just as before. It all works. Yep, phony targets. There's another phony target you typically see all to build all the targets in your program. There's one more I want to show that Dr. Gazillo actually doesn't like using, but I like to use for debugging purposes, not for production code. And definitely make this the last rule in your make file because this is one that you don't want to run automatically. It's called run. And we'll say it depends on main. And all we'll do with run is actually run main. So let me run make clean and then make run. And now we also compile and run our program all in one command. I think that's pretty nice. It helps you really quickly build your code, test it, and see if it's working, and then go back to developing. And to make this process even faster, heck, I don't even need a separate bash script here. I can exit tmux. I can do it all in Vim. Vim has, in the command line mode, so if you're in Vim and you press colon and type in make, it's built into Vim, I mean. You can run make directly from Vim. So I can run make clean. It'll run all those commands for me. I can run make run, and it'll run it all within Vim. And what's even cooler is that if I make a typo here, let's say I forget a semicolon, classic mistake, and run make, it'll print out the error, and not only that, but Vim will actually take me to where the error occurs immediately. Let me try making another error here so it's more obvious. Yeah, you can see it brought my cursor directly to the capital I because I made a typo. So some incentives for why you should be using the tools that we promote in this class, like Emacs and Vim. You don't need like a fancy IDE. It has all these features built into it. The only thing I've configured with the Vim right now is, I don't know if you've noticed, relative line numbering. That's it. You don't have line numbers by default, but you can add that very easily. You don't even need it. This whole make stuff that I'm showing is built in. So I encourage you to look into using the tools that we're sort of elevating in this course. Now, I'm going to spend the rest of today's lecture. Well, first, I guess I'll accept questions. Any questions on what we reviewed so far with make? Yeah?
Do you have like a cheat sheet for make, so like for those weird commands that people aren't used to using?
You'll want to look up the GNU make manual. So you can, I mean, you can see I've already been to this page before. All the GNU programs have manual pages online. And if you wanted to, you could also just use the man pages themselves. So again, man make, and you can see some decent documentation here with all the basic commands. But if you want to thoroughly understand all the different make intricacies, you can read the GNU make manual. And in practice, software projects will not use make alone. They use a set of tools called auto tools, which configures make for your platform, so for your operating system and hardware. This is necessary because all the commands I've defined so far on make, in my make file, they assume that you have GCC installed in your machine and have the RM command, which may not be the case if you're on Windows or on a different platform. So there are other build systems out there that are more complex than make that can sort of abstract these commands away into ones that are more generic. But for now, just worry about make. It's simpler, and we're all on used to this anyway on a Linux machine, so you only need make. All right, more questions? Yeah?
How is the dollar sign used specifically in Makefile?
It just says that what follows is the name of a variable. That's all. And the special ones I showed are special variables that make provides for you. They mean special things. But you can make your own variables in make. The dollar sign just means this is a variable. Maybe I'll open up the make file, show that. All right, so now I want to get started on the Hello project. Let me actually open up the course web page for it. So the big idea is that, so for this project, I know I said I won't require you to use Vim or Emacs for this course, but that's a little bit of a lie, because for this one project, I will require you to use Vim or Emacs. And that's only because we will be using a tool to record your output of your command line. And you have to use Vim and Emacs for that because they are command line editors. So maybe you can use Nano instead, but please try to stick to the instructions and use Vim or Emacs. All we're asking you to do is write a Hello World program. So you should be able to write this in like one go using one of these text-based editors. If you really don't want to learn anything new, just use Emacs because it's more similar to what you're probably familiar with like editors like IntelliJ or VS Code or Visual Studio or whatever you're using. So I'm just going to follow along in the instructions here. One more thing I want to mention. If you accidentally, yesterday working on the VC project, if you're working on it in class, and you accidentally named your directory COP-3402 fall 25, because that was what it was originally named and I forgot to update the name, you can fix that with a command. What command do you use to rename files? MV. Yeah, move. So if I made a directory here, by the way, if you want to remove a directory and make sure that it's removed, use FR. So force recursive. The mnemonic I use is for real. So remove for real. Remove that. Oh yeah, that's the image I showed yesterday. So let's say I have that directory COP-3402 fall 25. I could simply move this COP-3402 Spring 26, and that would, oops, I forgot to pass the source directory. And now I would just rename it to Spring 25. I'm going to remove that image. Okay. Yep. Force recursive is two different flags. So recursive means remove a whole directory tree. By default, RM will not work if you try to remove a directory that is not empty. But recursive says remove the whole directory tree there. And force means remove it even if it doesn't exist. Try to remove it. If it doesn't exist, it won't do anything, but it also won't emit an error message. This is useful in makefiles, like I showed earlier. So if you want to delete a directory from within a makefile recipe, you'll want to use FR. Yeah?
Other
Sometimes it is slow. Sometimes it does go down. But usually not for long. If it goes down for a prolonged period of time, I'll extend the project deadlines, but it shouldn't be down for long. And if you want to work on these projects on your local machine, you can. You just have to make sure to copy the contents over to Eustace after you're done. And the reason for that is because there's a key you will need to push your submitted projects to the grading servers, and that key is on Eustace. There is a way to copy that key to your local machines as well, but it's a little complex, and I don't want to spend class time going over that. So just copy your contents to Eustace and then push from there to the grading server. All right, let's see, where were we? So I'll just follow along with these commands. Make dir -p. What does -p do? Parents. So if I type in man, make dir, and then look at -p, it says parents. No error if existing. Make parent directories as needed with their files modified. File modes unaffected by any -m option. So m is something else. You can ignore that last half. It makes parent directories as needed. What I'll actually do is SSH into Eustace here. That way I'm kind of on the same playing field as all of you. And it might work. I'm not sure if it's still running into errors or not. If it doesn't matter. I'm on Linux, so it'll be mostly the same. I just can't push to the grading repo. Another reason to use Vim and Emacs that I want to bring up, especially Vim, is that Vim is ubiquitous. It is pre-installed on many Linux machines. And as I just showed, my Vim that I've installed here on my own machine, for when I'm giving examples, is barely configured at all. Yet I was able to access a slew of features from within Vim. Emacs does not come pre-installed on many machines, on Linux machines. So if you use Vim, you'll be more versatile, and you can log into remote machines and get straight to coding without needing to install your IDE or your editor of choice or all your plugins. You can just go in and immediately start coding as if you were on your own machine. So it makes you a bit more of a versatile developer. You don't have to use Vim as your main editor, but at least knowing how to use it makes it a lot easier for you to just go on somebody else's machine and get started working. This is taking a while, so I think I'll just, I think it worked, but then I exited. What I'll do is start this project on my local machine. Maybe what I should do actually is this. Here, this is probably a better idea. Run tmux, split my screen like I had done before. In this one window, I'll SSH into Eustace and get it started. And while it's logging in, it just worked. Guess that was all for nothing. Also, you have access to tmux on Eustace as well. So if you like how I'm splitting the screen and stuff, you can do that on Eustace. The machine, it's already installed. What?
Where on the website is the SSH Eustace tutorial? Like to shortcut Eustace?
Oh, that is.
I was looking for it back then.
I don't know if that shortcut is on the website. I can add it if you just Google. Actually, I can show you. Basically, you'll use this tool called SSH Keygen. Every person has a .sh, I'll have to open a new window here, directory on their Linux machines. So, I mean, this will only work if you're on Linux. At least these steps, I only know how to use them for Linux. So you'll probably, there's similar steps for Windows, but if I go into my .sh directory, which is a hidden directory here, and I'm going to grep, which is a search command, my config file, pass it a C flag for the context of 3 lines surrounding, and I'll search for Eustace. Basically, in this config file, I've configured a short name for my Eustace. This is the host name, this is the full path, this is my username, and that's a short name I'm using, so I don't have to type in the whole thing. You would create this, add this information to your .sh directory in your config file on your local machine that you're SSHing into Eustace from. Then you'd have to do some other steps that I'll provide later to configure the password so you don't have to enter your own password every time. I haven't done that actually. As you see, I still have to enter my password every time I log in. So, but this is all you have to do to get that shorthand working. Okay, so I'm in Eustace, and I'm going to follow these steps. So make dir -p cop hello cd hello get init. Oh, I'm running low on battery. I should be fine. And, oops, no, I don't want to open that up. What will this command do? This echo command? We talked about it last time in class. Yes. It redirects it into, so echo by itself prints out what you pass it, and then the less than or greater than symbol here redirects the output into a file.
Sorry.
Yep.
Just to ask, I'm trying to download Linux on my Windows. It's like a high-end gaming laptop. What distro do you recommend? 'Cause
I just use Ubuntu. It's pretty simple. I mean, you could use if you really want to configure things and learn how everything works, but you don't mind also struggling for a bit, use Arc because it doesn't provide you with as much to begin with. So you'll have to learn more information yourself. Ubuntu is the simplest just to get started. Yeah. So. Okay, so we have that README file. And I'll just copy and paste these steps, the rest of these steps. So it brought me to my editor, asking me to write a commit message. I'll just say initial commit. And now we should be good. So this created that remote repository for me to push my code to, and has committed my changes to my own local repository. So I'm all good to go. Now we're going to use this command here called script to record your steps that you're following for this project. So let me see where the script command, all right here is where we ended. So it's only a few commands. So I'll do this pretty quickly. The script command, if I look at the man pages, it makes a type script of terminal session. So it stores everything in your terminal session, all the outputs and whatnot, and then with the -t flag here, it says log timing file. I'm recording my timing information in hello.timing. This is so that you can actually play back your commands in real time and see them typed out in the same speed that you typed them in at originally. So if I run this script, this command here, now I'm going to make this hello.c file. I'll make sure it's correct. So main void printf. Actually, I think the instructions here are to type in hello world. I recommend copying and pasting it so you don't get it wrong because this is case sensitive. We're going to be grading it based off the exact case. So just copy and paste it. Don't do anything tricky here. Include studio.h. And let's see. All right, that should be it. Also, one little thing. The C manual actually says that the main function is special and that you don't need to add a return value to it. By default, main will return 0 if you don't specify a return statement. Now I'll GCC to compile this, hello.c, and then I'll run hello. And now I'll type in exit to stop recording. And we can actually play this back now. I'm going to pass nothing here. I'm going to remove that to argument. And you can see if I play this, it actually starts running the same commands that I just ran in real time. It's not actually running these commands. It's just playing back the terminal output. What was in the terminal? And if this is boring or too slow for you, you can actually specify a number to specify the speed. So if I say times 4 or just number 4 here, it runs at 4 times speed. The graders are not going to be actually running your scripts. We're just going to be running the commands in the scripts to make sure that you follow these steps correctly. And this is why we require that you use a terminal-based editor for this assignment like Emacs or Vim so that we can actually have this script command work correctly. All right, now we're going to make a makefile like we had made before, and we'll use capital M this time. Copy all this. This is pretty similar to what we saw earlier. There's 2 tabs here, which is interesting. Oh no, these are spaces. Interesting. Let me try and save that, and we'll see what happens. I guess it just works. I guess the leading spaces don't matter. Yeah. I'm just going to re-indent these because I'd rather have it all just be one indentation, one tab. Okay, and let's see. By the way, in Vim, save and quit, press colon, W, quit, save, quit. You can also press capital Z twice in normal mode, and that will save and quit. That's a bit riskier because you're kind of just like doing it immediately. You're not taking extra time to check that your changes are what you want to actually save. We can test our makefile, make clean, to run that, make it again. Oops. Oh no, my battery's almost out. Let me plug it in so my computer doesn't die. Where is there an element? Right here. Okay. Should be charging, I hope. So I gotta make sure that my computer does not die on us. All right, there we go, we're charging, okay. So now for grading, you're going to have to commit your changes to the your local repository. And we're going to practice good software engineering skills here and create separate commits for each file we're adding. So you could have added like all these at once, but it's better to add them in separate commits so that you can have individual, a log, like an itemized log of changes essentially to your program. So I'm going to add these, add a script, add recording, and then I'll add this one. Add makefile. And there's one more command here that I want to show. One more thing I want to show that I think I hinted at yesterday. Oops, I made a mistake here with my makefile. It's running rm. Oh, I mistyped phony here. There we go. So it was running rm after every time I compiled the program. I had to correct the typo with the phony rule to fix that. So I'll add that change. And you're allowed to do this in these projects. You are allowed to, keep pushing changes if you find that there's a mistake in your code. And you'll notice that if I run git status, you can already see it here. I'll run it again. there's this untracked file called hello. I think I showed this yesterday, but we don't want to track compiled files like binaries and executables. So the way around this is to add a file called .gitignore. And this will tell Git that there's certain files we want to never add to version control. And now if I run git status, you can see the .gitignore appears as an untracked file, but the hello file does not appear. So it's good practice to ignore your compiled, generated binary files, whatever they are, because the expectation is that your program's build automation system will build those for you and for your users of your software or other developers. You shouldn't have to commit this to version control. So now I'll run git add again, .gitignore, git commit. I'll just say add.gitignore. And remember, it's good practice to use like the imperative voice in commit messages or in their titles, like a command. And I can push all these changes. So if I run status, actually, you can see we're ahead of master by submission/master by 5 commits. So to fix that, I'll just run git push. And now it pushes all my changes to the remote repository. And let's see. Yeah, there's a self-check here. Let's see if we can get this self-check working. So I'm going to go back up a directory here. I'm going to run this command, git clone. So git clone is what you use when you want to create a copy of a remote repository that you do not already have on your own machine. If you have a local copy of a remote repository and you want to pull the changes, you'll use git pull. But if you don't already have a copy of a remote repository in your machine, you'll have to use git clone to create that initial version of the software, the initial local copy. So I'll run git clone here, and the second argument tells us where we want to put that clone. We'll put it in the temp directory, which is a directory that Linux machines provide by default. It will essentially it's like a directory that is like a trash bin. It's stuff that is not going to stay around forever. I think your operating system will delete contents of this directory regularly for you. It's good practice to put things that you don't plan on keeping for a while in this temp directory. And we're going to create a hello self-check directory in there. So now we can go into that directory. Let's see. It was temp hello self-check. There we go. And you can see we just cloned our remote copy of the repo. And if I cat out the contents of that make file or the hello.c file, you can see it has the same contents that we added earlier. So this is another local copy of that same remote repository in our machine. This is how the self-check works, because you're essentially verifying that what we see on our end in the grading server is what you see on your end. This is why you want to run these self-checks. Yeah, and you can run all these scripts to make sure it works. So again, we could run this command here to make sure that our script works. Hello self-check, I'll run it at 4 times speed again. Oops, no, right. I didn't copy it correctly. There we go. All right, and it still works. So it seems like everything was uploaded correctly to the grading server. I actually have commands to run the checks. Let me see if I can get those to work. I'm not sure if I can, but I will try it. So let's go back to, I think I need a local terminal window for this one. I'm going to try this. If it doesn't work, I'm going to stop, because I'm not sure if this will work or not, but I do want to show you all how we're going to be grading your projects, if I can get this to work. So grading, and I think it's, I open up the README here. Okay, -cop, it's hello grader, yep. that one. I'll put in my NID instead. It seems like it's working. If I can type my password correctly, that is. Oh no, this is Ghetto Light's password. I don't know what the Ghetto Light password is. So, unfortunately, I can't run this example. But it seems like it's working. You get the idea. This is what we'll be using to grade your projects. Just we have scripts in our own machines we just run to grade them all once they're pushed to their grading server. Any more questions? All right, I have office hours after this until 2 o'clock. Health Science 244, so please feel free to come see me then.
I've been having trouble with the